Hello, everyone. Welcome to our PackagingCon talk, where we'll do a deep dive into exactly what are container images and how cloud native build packs actually create them. My name is Sambhav Kothari, and I'm an ML platform engineer at Bloomberg. I'm also one of the maintainers on the cloud native Buildpacks project. Together with me today is Natalie Arellano from VMware, who's also a maintainer on the implementation team in the Buildpacks project, which is responsible for maintaining the lifecycle, which is the binary at the heart of all of this magic. So, what are we going to be covering today? First off, we'll start off with a quick introduction to what container images actually are. Then we'll do a quick case study where we'll explain how Docker Build, the tool which you might be most familiar with, actually works and creates container images. And this will nicely set up the stage for the final and most important part of this presentation, which is how build packs and lifecycle actually work. Ready? Let's get started. So what exactly are container images? Like everything else in the StarNext world, they're just files. More specifically, a file system bundle coupled with a config that our container runtimes know what to do with. Let's explore what that means with an example application. So here I have a really simple Python web app consisting of just 3 files. There's the application source code, which returns hello PackagingCon, a requirements.txt file, which lists out all the application dependencies, and a Docker file with instructions on how to build the output image. Now, if you take a closer look at the Docker file, we see it's fairly typical. We start off with a base Python image. We set a working directory, which will be the current working dir for all the subsequent instructions in our Docker file and the final container image. Then we copy off the requirements file separately. If you're familiar with Docker build and how it works, you'll know exactly why we're doing this and the intricacies that come with using Docker files. Next up, we're installing the dependencies using pip install, and finally copying the rest of our source code over and setting an appropriate start command so that when a container boots up, it knows the right command and entry point to start up. Now, if you try and build this Docker file, we'll end up with something that looks like this. This is just a cleaned up output from Docker inspect, showing what the image config blob looks like. It's basically a JSON blob consisting of a few key value pairs. What we're interested in are these 2 JSON objects, the config and the layers. First up, let's take a look at the config object. The config object describes certain properties of the output container, like what user to run as, what the working directory is, what environment variables would be set, and what the entry point command should be, among other things. If you look closely, you can see that we are able to map Dockerfile instructions to the values in the config object. This config object is necessary for container images in order for them to be run successfully, but a Dockerfile isn't necessarily the only way to construct this config object, as we'll be seeing later. Next up, we have the layers object. Layers are simply blobs that serialize a file system and file system changes into this concept. All these layers are content addressable, which means that you can locate and retrieve these blobs or tuples based on their content, which uniquely identifies them. And one or more of such layers are applied on top of each other to create the complete file system, which forms the basis of your container image. And this is what I mean by applied on top of. This is a typical overlay file system. You see there's a lower layer with files 1, 2, 3, and an upper layer with new versions of file 2 and 4. The final combined file system looks like the one you see at the very top. This is a very useful abstraction in container ecosystem, as it makes it possible to share file system layers and make modifications to them, while still making it possible to reuse the underlying base layers and images. And this is what forms the basis of the so-called base image. Now, if we printed all of those layer checksums, this is what we get. The output you see at the bottom is output from a wonderful tool called Dive that lets you inspect any container images and their contents. If you look closely, you can again see that we are able to map our Dockerfile instructions to the file system changes and the layers that we created. The first 5 layers that you see come from our base image, which is the Python 3.8 image. And then from then onwards, any Dockerfile instructions that lead to file system changes create a separate layer containing just those changes. For example, a workdir instruction created an empty /app directory at the root of the file system. Our copy file instruction copied our singular requirements text file into its own layer. And as for our pip install instruction, what it actually did was run the entire command, take a snapshot of all the changes that happened as a result of running it, and stored it in a separate layer. And this is typically what's happening under the hood when you're running all those run instructions. It is also why you'll see Docker files which try to chain multiple shell commands into a single run instruction, so they can put all of these things together into a single layer. This is not ideal for creating layers, but this simple generalization has worked well for Docker files. And finally, we see a last copy instruction, which copies over the rest of our source code, which is the app.py file, into its own layer. And that concludes the creation of a container image. So now that we know the core concepts behind what make a container image, let's take a peek at how container build, or in this case, Docker build, typically works. Before we get to Docker build using a Docker file, let's start from first principles and see if we can create a container image without a Docker file. Docker does expose this functionality using something called Docker commit, which allows you to take a snapshot of a running container, and it finds all the changes made to it compared to the base image. And then it stores all of those changes in a separate layer and allows you to tag it with a new container image tag. So let's see this in action. First up, let's create a demo container using BusyBox, a simple container image containing basic Unix shell utilities. Next, let's create a demo file which contains the contents hello world. And we run a cat command simply to make sure that the file is actually present and has the appropriate contents. Reminder, this is a running container and not yet an image. Finally, we run docker commit, which lets us save the current state of the demo container into an image called demo image. And that's it. Our demo image is ready. If we want, we can spin off another container using this image, and we see that the demo file is indeed present in our newly created demo image. Now, given this principle, let's see what Docker build does with Docker files. We have the same Docker file as earlier. And if we were to build an image out of this and check what Docker actually is doing by running Docker stats on the right-hand side, we'll find something interesting. So you can see Docker is simply running all the steps in your Docker file. But what's this? It's actually creating container images. It's actually creating containers and running the equivalent instructions in those containers. If you take a close look on the left, you see that the workdir instruction spawned of a container with the ID 9FE, and which is the same ID we see on the right-hand side. Similarly, if you scroll and skip a few instructions in a Docker file, we see that a run instruction and other instructions did the same. They created more containers, and they took a snapshot of them. So that's essentially what Docker build does behind the scenes. It's trying to create new containers with the instructions and commands that you provided. It commits those changes and creates a new image out of it. This provides a nicer and declarative interface over the Docker commit method, but these are all just different ways of constructing the final container image with its layers and config blobs. So just to recap what we've learned, if we were to really simplify things, container images are just layer tarballs and config files, and Docker build is just one way of ending up with this output. It's not the only way. There are other tools like Builder, Canico, and most importantly, Cloud-Native Buildpacks that can create images that can run on any OCI container runtime, which is practically every production cluster out there. Now, armed with this knowledge, I would like to hand over the presentation to Natalie, who will tell us exactly how Buildpacks build container images and how they unlock operations like rebase and independently cache build time only layers and other powerful rebuild functionalities, which you cannot even think of doing with something like Docker files. Over to you, Natalie.
Great. Let me share my screen. I want to share this one. Okay, you can see the presentation?
Yep.
Okay, great. All right, so let's talk about, sorry, just getting it. Let's talk about Cloud Native Buildpacks. So I think before we can talk about what is a Cloud Native Buildpacks build, we need to talk about what is a Buildpack. So a Buildpack is just a pair of executable programs and some metadata. And we'll talk a little bit about what each of those programs do in just a second. So Buildpacks need an environment in which to execute. They're usually packaged together with the lifecycle in an OCI image where the base image or build image provides the OS level dependencies that are needed by the Buildpacks at build time. A directory containing application source code is copied or mounted in. And then the lifecycle executes the Buildpacks that are provided and assembles the result into layers that are placed on top of a new base image, which is we call the run image. And that contains the OS level dependencies that are needed by the app at runtime. The lifecycle is a program that orchestrates the build, and it executes in a series of phases where each phase has its own distinct responsibility. So looking at those in turn, we start with the analyze phase, which gathers metadata from a previous build of the same image. This information is used to determine if layers from that previous build are unchanged. This avoids the need to re-upload data to the registry or the daemon, wherever the image is being stored. Moving on to the detect phase, if we recall that a Buildpack is composed of two binaries, the first detect determines if the Buildpack is needed or not. So it looks at the source code that is provided and determines if this Buildpack is applicable. So as an example, a Maven Buildpack might look for a pom.xml file in the source directory. Gradle Buildpack may look for a build.gradle file. And multiple Buildpacks can work together. Each Buildpack can provide its own distinct piece of build logic that's required, and together a final application is produced. The next phase is called restore. This phase is where we copy build time dependencies that were cached in a previous build back into the build container. The first build with Buildpacks might be a little slow depending on how many dependencies are actually downloaded, but subsequent builds can be much faster. The next phase is called build. That's where that second binary that's part of a Buildpack is executed. The build phase is where the logic that Buildpack is responsible for is actually performed. So things like downloading dependencies, running compilation steps, setting the start command for the image, setting environment variables, and more can be done by a Buildpack in its build phase. But very importantly, Buildpacks must follow the Buildpack specification, which restricts what Buildpacks are allowed to do, what file system locations they're able to write to, and we'll talk about why that's important in a bit. Finally, we have the export phase. This is where the lifecycle actually creates OCI image layers containing the compiled application and any dependencies that are needed at runtime. It places those layers on top of the run image that we mentioned to create the final application. There's no snapshotting here because we're simply creating tarballs and an OCI image config. Also, because of the metadata that was provided by the analyzer in the first phase, any layers that have not changed from the previous build will be reused, meaning that they will not be re-uploaded. And also any build time dependencies that need to be cached for the next build are saved during export, either to a local volume or a registry image as the cache repository. So all that being said, we want to come to a common myth that sometimes comes up about Buildpack's build, which is that a Docker daemon is required. This is not true. A Docker daemon is optional. So while the lifecycle itself must be run in a containerized environment, the lifecycle does not need access to a Docker daemon. It can export images directly to an OCI registry, or it can export to a daemon if that is desired. The analyze, restore, and export phases require registry or daemon access in order to reach the previous image, the cache image if an image is being used for cache, and the target image, respectively. So if the lifecycle is executed within a CI/CD system such as Kades, no Docker daemon is required. Just to touch on the other two phases, detect and build. These execute Buildpack code, and they run completely unprivileged as a non-root user, and they do not receive registry credentials even at the container level if the distinct lifecycle phases are run in a separate container, which is an option that we provide. The lifecycle, when executing Buildpack code, will strip out any environment variables that could be considered sensitive. So we really take a lot of care to sandbox Buildpack code as much as possible. So with that, I will give a demo, and I'm gonna exit full screen on my. I don't know if that worked. Did that work?
I still see that tab.
Okay.
Now I see.
I'll turn it off. Okay, so I'm gonna build. First of all, I just want to show where I am. I am in an app directory. So this app.py is the same one that Sam showed earlier. And I want to just pack build my app. Notice that I didn't have to provide a Docker file. I literally just had to provide this one command on the command line. Pack is a CLI tool produced by the Cloud Native Buildpacks project that enables that mounting in of the source code and executing the lifecycle that we talked about. So just taking a look at the output, you can see that this is the first time I've built the image. So no previous image was found. There are 5 build packs that are participating in the build. You can see that they're relating to Python for the most part. Nothing to do during restore because we don't have any build time dependencies that were cached earlier because there was no previous build. And looks like it's completed. Right, so you can see that this is where the lifecycle is doing all of the work of creating tarballs and adding them to the image. And here's where we add things to the cache. I just want to show that one more time just to demonstrate how on a second build, because now I've built this app before, we're restoring data that was cached previously, and it is actually much faster. Load. There, it's completed. So I'm going to hop back into the slides and hopefully give some more detail about what I can't find it. Where did it go? Oh, I'm so sorry.
It's okay.
That's fine. This happened to me too. Shall I remove your stream from the, shall I remove your screen from the live stream until you can bring your slides up again?
Sure. I really don't know where they went.
I know, yeah.
Well, I apologize. Let me go here. Okay, I'll just pull it up again. Sorry, everyone.
Yeah. There we go.
Oh, okay. Sorry, and now I'm in the wrong view. There's my demo. Okay, let me present. Oh, whoops. I prefer to have the. Okay, let's go over here. All right, let's continue. Hopefully. Okay, we can see this now, right?
Yeah, it's not in full screen mode.
Oh, sorry. There.
It's fine.
Okay. All right. Well, I'm sorry. I'll try to go a little bit quickly to just cover as much as we can. But I want to talk a little bit about the Buildpack API because that's very interesting. It restricts the file system locations that Buildpacks are able to write to. So namely, there are just 2 directories where they're really expected to make their changes. Those directories are called layers and workspace, and we're going to look at the contents of those directories as we do a build, just to see what capabilities are available to Buildpacks and how that affects the final image. So if I move on, this is showing the directory structure of the build container before any Buildpacks have executed. So we have the layers directory on the left, which is totally empty, and the workspace on the right, which just contains my source code. The path variable is inherited from the build base image that we talked about. And now we'll look at what happens after we run the first Buildpack or the first Python related Buildpack, which is the CPython Buildpack. You can see that it's made some changes to the layers directory. It wrote a subdirectory for CPython right here, and it also provided a configuration file, which is for the lifecycle to understand how that Buildpack wants the CPython subdirectory to be treated. In particular, the lifecycle knows that it can update the path, the library, cpath, and path variables to include the contents, whatever the Buildpack placed in the subdirectories of CPython. That's a nice convenience, a way for the CPython Buildpack to set up the environment for the next Buildpack to execute. I'm going to gloss over this Python path one real quick, but basically this Buildpack is setting up the environment for the next one, right? So that would be the pip Buildpack, and it does the same thing. It can add data, it adds configuration files for the lifecycle, it can modify the environment variable that was set up previously by prepending or appending or overriding. So this is kind of really illustrating how Buildpacks can work together and each contribute their own sort of very narrowly scoped piece of logic, how they can be composable. So finally,
I think you have 2 more minutes. Sorry for interrupting.
All right, I'm gonna go a little bit faster. I'm just gonna show basically the Buildpacks are able to say, hey, these layers are needed in the final image, and these layers I don't need them again. I just want to cache them. All of that kind of level of configurability is available. So if we look at the run container, we can see that only the dependencies that are needed at runtime are actually present. The lifecycle just the lifecycle will tar these up and put them in the image. And so that's what I'm showing here with the dive tool, which is really amazing tool, just to see how each layer in the image actually corresponds to a subdirectory, either a directory that was created by the Buildpacks, the workspace directory, which contains the source code, and this other component that the lifecycle has added, which we're going to talk about really quickly next. I'm showing the image config to demonstrate that the entry point is actually this CNB process web, which the lifecycle has set up. You'll notice that the environment variable that's hard-coded in the image config doesn't contain those variables, those Python path variables that we saw earlier. It's actually this other component of the lifecycle called the launcher, which is present in the application image. Which is responsible for sourcing the environment for the app. So the entry point is actually pointing to, it is a symlink pointing to the launcher, which is responsible for starting the app at runtime and sourcing the environment. And you might wonder, why not just hard code that in the image config? The answer is that this enables the image to have multiple processes with potentially different environments for each process. So that's a nice convenience of Buildpacks. this is just to summarize what we saw, right? Buildpacks can only write to 2 directories. They rely on Linux file system and NVAR conventions. The lifecycle is responsible for creating the final image, and there's a component of the CMB lifecycle that ends up in the final image, which is responsible for starting the app and creating the environment at runtime. Why do this? It can be faster. It doesn't require a separate container per run instruction. There's no need for snapshotting. A build pack can make changes to their logic without invalidating the cache for all build packs that follow in the build. So there's a lot more flexibility that's available. Builds all happen in user space. You have fine-grained control of the layers. And finally, it enables this feature called rebase, which I probably won't be able to get into due to time, but just suffice to say, the fact that we restrict those file system locations means that you can safely swap out a patched run image when necessary without having to rebuild your app. One limitation is, again, because of the lack of arbitrary file system changes, you can't do things like install operating system packages with Buildpacks. However, the project is currently working on something, a Buildpack-like extension model that would enable extensions to output Docker files that could be used to extend the build or the run base images prior to a Buildpack execution. So stay tuned for more information on that. With that, I invite you, please reach out. We love hearing from Buildpacks users, and thank you.
And thank you, Natalie and Sambhav. Unfortunately, we don't have time for Q&A, but I would think that Sambhav and Natalie are in the Element chat where they can answer questions.